Hello everyone, welcome to Dr. Ravi's Academy. In today's class, you will be learning how to draw the acceleration diagram of a 4-bar mechanism. Let us look at the problem. The length of the links are given. Here PS is fixed link, that is 200 mm, and PQ is a crank 62.5 mm at an angle 60 degrees with the horizontal link. QR is 175 mm and RS is 112.5 mm. The orientation of the angle is given and you can draw the configuration diagram to the scale. So, after drawing this particular diagram, so he is asking what is the angular acceleration of link RS. RS is this is nothing but your output link. So, in order to calculate the angular acceleration, first of all you have to draw the velocity diagram. So, for this given configuration diagram, the velocity diagram you have to draw, and the angular velocity of this particular driving link is given 10 radians per second. So, you can calculate the velocity of link Q with respect to P. You can calculate it is R omega. R is nothing but the length of the link in meters, that is 62.5 divided by 1000, that is in meters, multiplied by the angular velocity, that is 10. So, you are going to get it is 0.625 meters per second. This is the velocity of the crank, that is QP. The direction is known and the magnitude is also known. So, you can draw a vector along this line. So, let us adopt a length of this is equals to 10 centimeters. The length of this is, you can call it as QP, length is 10 centimeters. So, here P is your beginning point, let us call it as small p and small s, both are the ends of the fixed link, and let us draw a line, a vector of 10 centimeters length. So, this indicates your QP, the velocity of the driving link. The magnitude is known, that is 0.625, that you have taken it as scale, then the scale becomes, it is 1 centimeter is equals to 0.0625 meters per second. This is the scale, right? And you know the direction of the velocity of this particular link, that is RS, with respect to this link, it is perpendicular to it. The direction you know. So, draw a line whose direction is known, and after that the direction of the same point with respect to Q, it is perpendicular to it. So, passing through Q, erect a vector perpendicular to it, and this is what is exactly the required point, or intersecting point is R, and this is, you can measure these lengths. Here the length of RQ is, by measurement you are going to get 5.5 centimeters, and of course this is 10 centimeters, and this length is 6.8 centimeters. So, that is by measurement. After measuring this, you know the velocity of all the links, you can proceed to calculate the normal component of acceleration. This completes your velocity diagram. After knowing the velocity of each and every link, now to calculate the velocity is what you have to do, you have to multiply the 6.8 with the 0.625 meters per second and 5.5 into 0.0625 meters per second, so that you are going to get the velocities. And these velocities you can write down, it is velocity of, as you know, QP is, that is input velocity, that you got, it is 0.625 meters per second, and velocity of RQ is this link, RQ is 5.5 into, it is 0.34, you are going to get 0.34 meters per second, and finally the other velocity of RQ, that is RQ length is 5.5, and if you multiply with it is with this length RS. RS is 6.8 and it is 426 meters per second. So you got the velocity of the all the links. After knowing the velocity of the links, let us proceed to calculate the normal component of acceleration. As you know, the normal component of, I am using a symbol A subscript n for normal, which is also known as radial component of q with respect to p. The direction is in the direction of p. So this value is velocity square, v square by r. V is 0.625 whole square by r is the length of the link, that is 0.0625 in meters. So this gives you the magnitude of the normal component of acceleration of q with respect to p is 6.25. 6.25 meters per second square. This is the normal component of acceleration. Alpha is not given, the angular acceleration of the driving link is not given, that you can take it as 0. Now let us calculate the normal component of acceleration of this particular link. So that is v square, velocity, you know, velocity is rq, it is rq, that is 0.426 whole square by length of the link 0.175, it is, you are going to get 0.634 meters per second square. And finally, the angular or the normal component of acceleration of rs is v square, velocity of rs, that is 0.34 whole square by length of the link 0.1125 in meters. So that gives you, that length gives you, it is rs is 1.6 meters per second square. Meters per second square. Now you know the normal component of acceleration of a q with respect to p, magnitude is 6.25, and you know the normal component of acceleration of r with respect to q, 0.634 meters per second square, as well as the normal component of r with respect to s is also known, the direction is toward this and the magnitude is 1.6 meters per second square. Now you know all the values of the normal component of acceleration. Now you proceed to draw the acceleration diagram and let us adapt a scale. It is a point that is acceleration, normal component of acceleration of q with respect to p is 6.25 meters per second square, that you take it as 10 centimeters length. That means 1 centimeter becomes, it is 0.625 meters per second square. This is what is your scale. So the direction is towards towards p. This is the direction, and magnitude is, you have taken 10 centimeters, which is equivalent to, it is 6.25 meters per second square. So here you are going to get the other end, that is acceleration of, you can call this as pole, that is p prime and s prime, both ends of the fixed link, and this is what is your q prime. So the acceleration image of driving link is drawn. Now let us proceed to the acceleration of r with respect to q. Direction is towards q. So this is the direction. Let us adapt the direction, and length, you can calculate the length is acceleration of this particular link is 0.634 divided by 0.625, you are going to get almost 1 centimeter. So you can take it as 1 centimeter length, 1 centimeter, and you are going to get this x point. Intersecting point is called x. After locating this point x, erect a perpendicular to it, because your tangential component will be perpendicular to it. This is 90. Leave it. Now let us proceed to the output link rs. The normal component is toward the center, and the acceleration is 1.6 divided by the scale factor, that is 0.625. You are going to get this particular length as 2.56. Let us erect a line along this line, and at a distance to 2.56 you have y point, and erect a perpendicular to it, and where it intersects, that is your required point r, and this is your tangential component, and joining these two is your resultant, that is total acceleration A, and joining these two is also total acceleration A. Now you got all the components. Here what is that is required? You want to calculate the alpha, that is angular acceleration of RS. To calculate RS, you need tangential component of acceleration of RS. So this is what is your RS. Measure this length, that is R prime, you can call yr prime. If you measure that particular length, you are going to get it is yr prime as 8.5 centimeters length, and with you, if you multiply with the scale, it will be 5.3. If you multiply with the 0.625, it is 5.3 meters per second square. This is your tangential component of output link RS. Is asking angular acceleration. I will get angular acceleration. So angular acceleration alpha is equals to the tangential component of output link divided by the length of the link in meters RS. This gives you 47 radians per second square. This is your required answer. Radians per. The angular acceleration of RS is, it is tangential component of acceleration divided by, it is R alpha. R is nothing but length of the link, alpha is angular acceleration. So RS is length in meters, that gives you 47 radians per second square. I hope you understood this particular problem and you can start practicing this particular problem. Thank you.